Let's discuss stability of equilibria in physical systems. Most potential energies are continuous and differentiable, so you can write a Taylor's expansion of the potential about some equilibrium point x naught. Now, about any point, in fact. If the point is an equilibrium point, in addition, the definition of equilibrium is that there is no force, and the negative derivative of the potential is the force, because F equals minus gradient of u. Now, even though I wrote this as gradient in one dimension, it just reduces to negative du by dx. This, by the way, applies in any number of dimensions, and I have provided the generalizations in my notes using Morse theory. But for this video, we'll just stick with one dimension because the discussion is rather simple in one dimension. Now, we are also going to assume that higher order terms go to 0, which means that you're just left with this one term and a constant term. So that's a useful simplification in the vicinity of an equilibrium point. So if an equilibrium point x naught exists in a system, the potential can always be written as some constant value, which is usually scaled away to 0, plus 1/2 k times x minus x naught squared. Now, I wrote this double derivative of the potential purposely as the spring constant k, just to show you that nature really is a bunch of springs. So once you have now when is the spring constant an actual spring? It's a spring constant only if k is bigger than 0. Otherwise, you don't have a spring. You have a negative value of the spring constant, makes no physical sense. So k bigger than 0 actually is a good requirement for a physical system. And you can think of it as also the criterion for a stable equilibrium. If k is less than 0, nature doesn't like it, and it's unstable equilibrium. It is possible for the spring constant to be equal to 0, in which case we have to go to higher order terms. You can no longer set the higher order terms equal to 0. You have to keep going till you get a term that's not 0, and that becomes your higher order spring constant. We won't deal with those types of anomalies in this video. So what I would like to do is just take a simple example and show you how to analyze it for stability, etc. So let's take this following simple potential. U of x is equal to ax squared minus bx4. So the first thing you need to do is plot it. It makes the analysis very simple if you know beforehand what to expect. So let's plot this. That's u of x versus x. X takes both positive and negative values. However, it's an even function because of the square. So we expect a good deal of symmetry in this problem. When x is 0, the function becomes 0, and it's also positive. Now, we don't know the true relationship between a and b, but for now, let's assume that a and b are both bigger than 0. When x is close to 0, x squared will dominate x to the 4. So definitely, this curve will have some tendency to do that. Now, eventually, at large values of x, the x to the 4 is going to dominate over x squared. So at large values, you definitely want to go negative, which means that there is some point where it crosses the x-axis, which also means that there should be a point where it attains a maximum. So all this we got by just examining the asymptotic behavior of this potential. The exact values where it plunges to 0 can be found by simply solving the equation u equals 0. And if you did that, you'll get an equation that says x squared times a minus b. So this is what I'm doing. I'm setting u equal to 0. Bx squared equal to 0. And that tells me that x equal to 0 is a double root. That makes sense because it's curving up. And x equals plus or minus square root of a over b are the points where it plunges to the negative zone. Now what about these points where it achieves its local maximum? That can be found by setting the first derivative equal to 0, and that is how you find the equilibrium set. So for equilibrium, you demand that the first derivative u prime x equal to 0, and that's going to be 2ax minus 4bx cubed. Well, if you set that equal to 0, you can factor out an x, so that will tell me x equals 0, or 2a minus 4bx squared equal to 0. One of those two conditions must be satisfied. Well, this condition gives you this equilibrium point here. If you keep a ball here, it will roll back and forth, so that certainly is a stable equilibrium point. And this gives you the unstable equilibrium point, because when x equals plus or minus square root of a over 2b, I've cancelled out the 2's, then you get the unstable equilibrium. So what I'm going to do now is write this, that's the negative square root of a over 2b. None of this is to scale, so don't hold me to that. Okay, and these are unstable. If you keep a marble there, that marble is certainly going to roll to the left or the right, and the same here. The marble is going to roll. So we have one stable equilibrium and two unstable equilibria. So let's write down the equilibrium set. It is x equals 0 plus or minus square root of a over 2b. And just by looking at the diagram, we already know the stability, but however, there's also an independent way of figuring out the stability, and that is to take the second derivative. So let's take the second derivative, u double prime of x, first. That's going to be 2a minus 12 bx squared. Now we're going to put, at each equilibrium, we're going to put the value of x here. So let's do u double prime of 0 first. U double prime of 0 is 2a, and since a is presumed to be positive, that's bigger than 0, so we have stability there. So independently, we found that that's stable. And u double prime at either a plus or minus a over 2b, it doesn't matter if you take plus or minus because you're squaring it here, is going to be 2a minus 12b a over 2b. So that's essentially negative 4a, which is less than 0 because a is presumed positive. So these are definitely unstable. Now once you have a stable equilibrium, you have a spring constant. That's what nature buys us. When you have stability, you automatically have a spring constant. And so we also, in doing the stability analysis, we have actually found out that there's a spring constant. So we can write the potential u of x. Now x minus x naught is 0 in this case. So these are the x naughts. U of x is equal to u of x naught, which is 0, plus 1/2 the spring constant kx squared, where k is equal to 2a. Let me now talk a little bit about the frequency of oscillation of the system very close to the equilibrium. By Newton's second law, well, actually, let's take the second law approach is fine. F is equal to negative derivative of the potential, so I get F equals minus du by dx. So this tells me that mass times acceleration, which is the double derivative of the position, is equal to negative kx. I'm not putting the value for k yet. So this gives me, if I divide by m and bring over the kx to the other side, x double prime plus k over m x equal to 0. So we can identify the simple harmonic oscillation frequency as the square root of k over m. So in our particular example, it's going to be 2a over m. And so that's the frequency of oscillation, or in many problems, that's the resonance frequency of a process. So those are valuable physics or chemistry or material science informations that you can take away from just a basic analysis of potential. I would also like to talk about large-scale motions now. When you have large scale motions, you can no longer approximate the potential like that. You have to take the entire potential. So for example, let's take a total energy, but we'll keep the total energy within bounds. If I have the total energy over here, it will not be good, because then the particle will never want to be in this region. But if I keep the energy under this, then the particle will know not to go over these hills. So it's like it'll just play in these valleys. Okay, so let's keep this energy E naught to be like that. If you have a negative energy, then of course the particle will not even move. So you need to have a positive energy, but less than the energy required at the unstable equilibria. The potential value at the unstable equilibria should be your maximum possible energy. Now if you have that, then I can write the total energy E naught as the kinetic energy, which is 1/2 mx dot squared, plus the potential energy U of x. So what I can try doing now is to find out where it stops. Now it's going to stop, if it's oscillating, it's going to stop at the end points. These are called the turning points, x minus and x plus. They're so named because the motion turns around. Let's try to find the turning points. I have to set x dot equal to 0. So basically that means the potential U of x must be equal to E naught is a condition for turning points. Let's solve this equation. Now this is unfortunately a quartic equation, but fortunately for us, this quartic equation is actually a quadratic equation in disguise, because I can set x squared equal to u. So if I make that substitution of x squared equal to u, that's just your friendly neighborhood quadratic. And you can solve that by taking the bu squared to the other side. I don't like having this coefficient of u squared negative. So I get negative au plus E naught equal to 0. And then you solve it just like you did in high school. So u, which is equal to x squared, is negative b, which is in this case is a plus or minus b squared, minus 4ac. That's going to be 4 E naught times b divided by 2a, which in this case is b. Now we require that x squared must always be bigger than 0. So what we can do here, this is certainly bigger than 0, smaller than a squared, so both solutions are allowed. But since x squared is bigger than 0, when I take the square root, I only keep the plus, have the, actually this, wait a minute, I think I made a mistake here. B squared minus 4ac, that's a negative ax squared minus bx4 equal to E naught. So I take the b there, I take the a there, so that's correct. Minus 4ac. Yeah, this is this looks good. This looks good to me. So what's going to happen here is that both solutions are allowed, and then when I take the further square root, I'm going to get plus or minus the square root of a plus or minus the square root of a squared minus 4 E naught b over 2b. So there are 4 solutions. How is that possible? Well, it is actually possible if you extend this all the way to the right. Then you'll notice there are 2 more solutions on this side, but we don't care about them. They're the other side of the hill. So we'll exclude those solutions and keep only the solutions that matter to us. So to keep the solutions that matter to us, I need the smaller value. So the turning points x plus minus are actually plus or minus the square root of a minus the square root of a squared minus 4 E naught b divided by 2b. Okay, so that's the 2 turning points. Now once you have the turning points, you can actually find out many other interesting things. You can find out, for example, the time taken to oscillate back and forth once. So for that, what I do is I write the x dots in terms of everything else. So x dot, when you solve for it, I'm going to get square root of 2 over m, the energy minus u. And x dot is dx by dt. So I can actually solve for time. So dt is going to be dx divided by the square root of 2 over m e naught minus u. And the total time taken to go back and forth between, let's say, x minus and x plus, which I'll call half the period, is given by this. Now usually this is a very complicated integral, typically an elliptic integral, so we won't be able to solve it until we talk about elliptic integrals later on. But in this particular example, it's not a bad integral. It is the Jacobi integral of the second kind, and we'll talk about that when we get into elliptic integrals.